comes fully into view. Welcome. Today, we're going to make sense of Big O notation, the shorthand computer scientists use to describe how an algorithm's running time or memory needs grow with its input size. Think of each colored panel you're about to see as a snapshot of one speed class. I'll guide you through the 9 most common classes, moving left to right and top to bottom. Shadow 1, constant time O1. First up, the deep brown panel in the upper left. Constant time means the work never changes, no matter how much data you feed the algorithm. 2 everyday examples are indexing directly into an array and inserting a key value pair into a hash table. Whether the array holds 5 numbers or 5 million, grabbing the element at index 3 still needs exactly 1 step. Linear time ON. Slide your eyes to the royal blue panel. Linear time algorithms grow step for step with their input. Scan an unsorted list to find the maximum, or check whether a target value exists. You must, in the worst case, examine every element once. Double the data, double the work. 3. Logarithmic time, O log n. Now the bright yellow panel. Here, running time ticks upward only as the logarithm of the input size. Classic example, binary search on a sorted array. Each comparison chops the remaining search space in half, so the cost climbs very slowly. Even massive datasets can be searched in mere handfuls of steps. Balanced binary search trees enjoy the same advantage when you insert or look up nodes. 4. Quadratic time O n squared. Dropping to the middle left purple panel, we find quadratic time. Algorithms whose work equals the square of the input size usually nest one full loop inside another. Think bubble sort, selection sort, or a double loop that prints every pair of indices. 10 items require 100 operations, 1,000 items, 1,000,000. Har 5. Cubic time O n pue. In the fiery red panel at center is cubic time. Some dynamic programming tables and the naive algorithm for dense matrix multiplication fall here. Each extra factor of n multiplies the effort dramatically. 10 items need 1,000 steps in quadratic time, but 10,000 steps in cubic. 6. Linearithmic time, O n log n, sliding to the neon green panel, the sweet spot many efficient algorithms strive for, linearithmic time. Divide and conquer sorts such as merge sort, average case quicksort, and heap sort break a problem into halves, giving the log n component, and then touch every element once per level, the n component. The result scales far better than quadratic, yet remains practical for huge inputs. 7. Exponential time. On the bottom row, leftmost teal panel, we hit costs that balloon frighteningly fast. Exponential time algorithms double their work with each extra element, typical of naive brute force recursion. Classic illustrations include searching all subsets for the knapsack or traveling salesperson problems. Great for tiny inputs, impossible beyond a few dozen items. 8. Factorial time. Next, the steel gray panel. Permutation generators that list every possible ordering land in factorial time. Even a modest set of 4 elements explodes to 24 permutations. 10 elements leap to more than 3.5 million. Factorial algorithms are the last resort when no clever pruning or dynamic programming shortcut is available. 9. Square root time, O(n). Finally, the magenta panel on the bottom right. Less common but quite useful, square root time shows up when you limit your exploration to factors or ranges. The sieve of Eratosthenes marks off multiples only up to clue n to find all primes co-n, and block-based search tricks use the same idea. Closing. So there you have it, 9 speed classes, from lightning-fast constant time to glacial factorial time. Mastering these mental yardsticks helps you spot which algorithms scale, which ones break, and where you should focus your optimization efforts. Thanks for joining this tour of Big O Notation 101. May your future code run fast and your complexity charts stay in the green.